Hello Year 12s and welcome back to Mathematics. Into this video we're starting our next topic of modeling financial situations. In the previous topic we looked at the sequences and series, and at the end of that topic we actually had a look at a few particular series that we could add together. So for example, we looked at the sum of a geometric progression, and we noticed that when we have a GP, the sum of a geometric progression, let me just erase this, sum of a geometric progression for a GP was a times r to the power n minus 1 over 1 minus, r plus r minus 1. And so we use this to actually sum up terms in our geometric progressions. What we're doing in this topic is actually applying stuff like this. So in particular, we're going to be looking at the sum of a geometric progression and solving for problems with geometric progressions to a few situations that deal with money. And in particular, when we've got compound interest and other scenarios where interest is involved. Now, if you're not sure what compound interest is a type of interest. So when you get paid money, when you lend or borrow money, and compound interest is one of those forms. For example, if you have a bank account. And so if you have a bank account, you might put, let's say, $1,000 in your bank account, just as an example. And then your bank will be like, okay, I'm going to give you 6% interest. And so if they give you 6% interest, you add on 6% of that $1,000, which is just $60. And then in the next period, you get $1,060. What compound interest does is that it keeps calculating this 6%, not based on the starting amount, but calculates the next 6% based on this new amount that you get. And so when we keep doing this, we add on another 6% based on this amount. And so instead of adding 60, what we're going to do is we're going to actually add on, and this is the part where I haven't done this in advance, we're going to go 1060 times by 0.06, and we add on another 63, so add 1060, so we get $1,123.60. So that's what compound interest is. And in this section here, we're going to actually look at a few problems with solving a few problems with compound interest, and also actually having a look at a few ways that we can calculate compound interest a little bit easier. I'm just going to adjust my mic, sorry. Okay, so that's what we're going to be looking at in this section. Now, first of all, before we do any of that, we need to actually introduce a bit of terminology. So, definition 1. Future value. Now, future value of an investment is the total value of the investment at the end of the term of investment, including all contributions and the interest earned. So when we talk about future value, what this means is, let's say we invest this $1,000 for 5 years. The future value is just what is the amount at the end of 5 years? What's this final amount? And that's our future value. Future value is just the amount at the end after however long you've invested it for. So here, let's say we've done it for 5 years. We just want to see how much money is in the account at the end there. Now here, there's actually two things to note. So this includes all contributions and all interest earned. So here, every time we're adding on a new amount of interest. So this one we added $60. This time, I think we added $63.63. So the future value includes all of that interest. But not only that, we're going to have a look at later on in this topic scenarios where people make contributions to the account. So all contributions. Now, in this topic, we talk about scenarios where when instead of just letting your money sit there and just like accrue interest without adding on extra money, often what people do is they put money into the bank account, the savings account. And so, for example, you might get 6% interest, and then after 1 year, you might go, okay, hang on, I'm going to add on another $1,000. And so here, instead of it being $1,060, it would actually be $2,060. And so future value in those scenarios also involves all of these contributions and how they actually change the amount of interest that is calculated. So that's what future value is, the amount that's at the end. Now, the other term that we need to know is what present value is. And here we go. Present value. Now, present value, so PV, is the investment of an investment is the single amount, if invested at the same rate for the same period, would give that future value. This can also be understood as the initial value. And so the present value is just what amount do we start off with at the beginning. So here, this is the $1,000. This is just your present value. So our starting amount that we get before the end of the investment. So present value, you can think of it as just the starting amount or the initial value that we have in the account. Okay, so this is a few bits of a terminology we need to know that we actually can apply in this section of compound interest. So let's flip over the page and let's have a look at this first section here. So laws and results. Generally, so in general, if you want to calculate future value, the formula that you would use is just present value plus the amount of interest that you accrue. So here, I is the amount of interest that's earned. So the additional thing to know about this is actually we can rearrange this for interest. So if we want to just find out how much interest there is, well, if we rearrange this, that's just future value minus the present value. So if you want to figure out how much interest you earned on your account, that's just your present value, future value minus your present value. Now, often we're not going to be using this formula as much to actually solve problems. We might be using this one here, this rearranged form, to actually think about, find interest in particular. But this first guy here is just for you to conceptualize, actually, my future value is just my present value plus however much interest I get over time. The formula that we will use quite often, and I believe this is on your reference sheet, so I'm actually going to check this right now. I should have checked this in advance, but this formula is on your reference sheet. Here, the compound interest formula is the future value is equal to, so here, this is the formula we're going to look at. Future value is equal to the present value, so PV, times 1 plus R to the power N. Now let's just talk about R and N here. So R, if you have a look, this is the rate of interest per compounding period. Now, this is the interest rate that you're going to get. So in that example I gave, 6% would be your interest rate. Now, the important thing here is this is per compounding time period. So what we need to actually check is how often is this compound interest being calculated? Now, what I said in the example above is that we're compounding it every year, but sometimes in some banks they offer that you get they calculate your compound interest every month. And so what we need to do is that we need to actually change up this interest rate to match the fact that we are compounding every month. So this is where this per compounding time period is actually really important. And this is expressed as a decimal or a fraction. So often they'll give you it as a percentage. What we want to do is we just want to rewrite it as a decimal. So like 0.06, for example, for 6%. So if I have 6%, I just want to rewrite it as 0.06, for example. The other thing is N. N is the amount of time periods. So if you have 1 year, that's just N is going to be equal to 1. But if the compounding period is every month, we need to actually make that match up. So for example, if they're compounding every month, 1 year the N value isn't going to be 1, it's actually going to equal to 12 because there's 12 months in a year. And so every month you're going to do a new compound. So there's going to be 12 periods. Now, there's another note here. There's another letter A, and I haven't actually introduced you to this concept A, because on your formula sheet, you actually have this formula, but doesn't look quite like this formula here. If you have a look on your reference sheet, there's a section on financial mathematics, and there's a formula there which says A is equal to P1 plus R to the power N. And this formula is exactly the same as this future value, present value formula. These are exactly the same. So instead, future value is just the same as the amount that you get at the end. P also stands for present value. So here, this P is going to be the same as present value. And everything else is exactly the same. 1 plus R to the power N. So this is the formula that we're going to be using to calculate compound interest. So if you have a look underneath, I've already highlighted a few of these notes. Important note, remember to divide the interest per annum. So per annum just means for every year, by the appropriate factor to place it on the time unit as the compounding period. So this is where we need to read the question carefully. They might say, for example, they give you 6% per annum, but it compounds monthly. So for example, e.g., 6% per annum compounded monthly. And so what we need to do is we need to actually find the associated monthly interest rate by dividing and scaling it to the appropriate time unit. So for example, that would mean that I need to go, okay, 6% per annum, I'm just going to write that as a decimal, that's 0.06, and I need to go the compound interest per month, and so I just need to divide that by 12 because there's 12 months in the year, and that is now the interest rate per month. So 0.06 divided by 12 is the per month interest rate. Okay. So that is the concept of just adjusting our per annum interest rate in order to match our compounding period. Underneath here, we've got another definition. So the future value interest factor. So here, the future value interest factor, they've got a shorthand for this, is the amount to multiply the present value by to obtain the future value. So in the compound interest formula, this section here, this 1 plus r to the power n, it's just your future value factor. And so it's just what you're multiplying the present value by. Okay, a few things to note. I'm going to get my notes out here. Okay. When you graph a future value, compound interest in particular, what happens is, this is an example of what happens when you graph compound interest. So over time, if you can think of each of these dots as after each kind of investment or compound period, this is the amount of money that someone has. The general graph is increasing exponentially. So it's an exponential increase, exponential. And so as you graph this over time, it becomes like that exponential graph. There's a few things to note about this exponential graph and things that will affect what the shape of that exponential graph looks like. So the more frequent compounding periods, so if you have more frequent compounding periods, so let's say you have an account that is compounding every year and you've got an account which is compounding every month. The monthly one is compounding faster because you're doing it 12 times over the year. They might have a lower, so they might be, so for example, it might be 6% per annum versus, and it was like, I think it was like 6% divided by, so 0.06. 0.06 divided by 12 per month. So this would just be 0.06 actually. The one which compounds more often will result in a faster accumulation of interest. So if you do more compounding periods, what this would look like is that your graph will be steeper and your money grows quicker and quicker and quicker. So the more often you do your compounding, the more often you have those compounding periods, the quicker your investment will grow. That's going to be helpful, particularly when we're trying to identify the graphs of particular compound interest investments. Okay, so that's something that we're going to know. So the more frequent you get for the compounding periods, faster accumulation of interest. So the more interest you're going to get over time. Okay, so let's just do a few simple calculations and apply this formula. So this is from a general maths paper because this is actually a common topic that Mathematics Advanced and also Standard 2 will actually sit in the have in the HSC. So sometimes it might actually have common questions between your paper and the Standard 2 paper. Okay, so let's have a look at this question. Pauline calculates the present value. So here, instead of using PV, they've actually called it N of an annuity. The interest rate is 4% per annum. It's compounded monthly. In 5 years, the future value will be $100,000. Which calculation will result in the correct answer? So here, if you have a look, we want to find what the present value is for this particular scenario. Now, what we're going to do is we're going to have to actually use the compound interest formula. Now, before I actually do any of that, let's just have a look at what information I get given. Well, we want to find this value of n. So we don't know what n is, the present value. So I'm just going to call this PV. We don't know what it is. In this case, it's actually called n. These are the exact same thing for this question. What do we know? Well, they tell us that the interest rate was 4% per annum. So I'm going to write here 4% per annum. Great. But the following part is it's compounded monthly. So what I need to do is I need to actually adjust this per annum interest rate to make it a monthly interest rate. So what I'm going to do is I'm going to actually need to divide this 4% by 12 because there's 12 months in a year. So I'm going to write this at 0.04 because 4% is just 0.04 as a decimal. I'm going to divide that by 12 in order to get that per month interest rate. So, so there we go. Okay. And what else do we get given? In 5 years' time, the future value, oh, actually, I ignored one other thing, 5 years' time. So here, we know that the number of periods, we've got 5 years. Now, if you have a look, we need to make sure that our number of periods matches up with the compounding period, the compounding kind of frequency. If you have a look, it's compounded monthly. We've got this 5 years. They do not match up. And so what I need to do is actually make them match up. So I need to write 5 years in terms of months. And so that's just going to be 5 times 12 months. There's 60 months in 5 years. And so here, the value of n is not going to be 12, but actually going to be 60. And the final thing is, the question tells me that so this is for n, this was this part over here. This is per monthly, was that compounded monthly bit, and it's going to be 5 years. And so that is the n value. The final thing that they tell me is that the future value is equal to $100,000. So what I can do is or if you remember from the alternative way of writing it, that's A is equal to $100,000. So what I can do is I can write down my compound interest formula. So A is equal to P 1 plus R to the power n. I can sub in all these values. So the future value was $100,000. So I'm going to write here on the left-hand side, 100,000. And that's equal to, well, the first thing is, I don't know what the present value is. So I'm going to leave that there. So I'm going to put P. You could also write that as n if you would like for this particular question. And actually for this particular question, I'm going to write that as n because that's what they've noted down as the, that's what they've noted here is the present value. I'm just going to write it as n just to match this question. I'm going to write here 1 plus the rate, which we found over here was 0.04 divided by 12. So 0.04 over 12 to the power of, well, the value of n that we found was there's actually 60 months because we need to match up our interest rate with the compounding period. The number of periods with the compounding frequency. So here, that's just going to be to the power 60. And so what I can do is I can start to rearrange this for n. So n is just going to equal to 100,000 on the left-hand side divided by 1 plus 0.04 over 12 to the power of 60. And so I'm going to have a look at which one of my answers this is going to be. Well, immediately I can get rid of a few. So all of them have this fraction 100,000 over something. I'm just going to look at what the future value interest factor is at the bottom. So here, for these this one over here in A, well, that doesn't quite match up because I haven't actually, this one hasn't adjusted. So notice here, this one hasn't adjusted the interest rate to match my compounding monthly. And the second thing is they haven't actually adjusted the power 5 to match that compounding monthly thing either. So this is gone. Second thing is, once again, this one hasn't adjusted the the interest rate to make it monthly. So this is also gone. And finally, the one at the bottom here, B, well, they've adjusted the compound interest rate, which is good. So they've divided that by 12. But if you have a look at the number of periods, the number of periods is still 5. It should be 60 here because it's not 5. We're compounding it monthly. We're not doing it for 5 months. We're actually doing it for 60 months to make that 5 years. So here, this B is gone. And so we're left with D as the final answer. So the answer here is going to be D. Okay, so that's just a simple calculation using that compound interest formula to help us answer this particular question here. Okay, let's have a look over the page. So with this question, all you really need to do is just substitute your values into your into this formula. The only thing to note is that we want to be really careful with how regular the compounding period. So is it monthly? Is it Is it monthly? Is it yearly? Is it daily? Sometimes you might get a question where it's like compounding daily. And so we need to make sure that our interest rate, so that first line over here, we need to make sure that our interest rate matches up with that. The second thing is, once we've gotten the correct interest rate, we need to also then make sure that our number of periods matches up with that. So here, if they give us how many monthly, we need to change our 5 years to be actually 60 months. So we can match up our compounding period, our compounding frequency is a better way of thinking of it, compounding period to with our compounding frequency with our compounding periods. That's what I mean. Okay, cool. Let's have a look over the page. Example 2. So this was from the HSC sample paper from last year. So let's have a look. The graph showed the future value over time of $P. So we've got a present value, P dollars, which is invested at 3 different rates of compound interest. Which of the following graphs identify each graph? So if you have a look here, we've got a few graphs. The first one is W, which is a little bit higher than the second one, X. And the final one is Y, which is quite a lot lower than the other two. What we want to do is figure out which compound interest each of these represent. So if you remember, there's two things here. Two things. One, two things that you can think about. If you have a higher compound interest, it's going to look like a steeper graph. If you have a more frequent compounding period, it's also going to give you a steeper graph. So if you have an increase in a higher interest rate, would mean that it's a steeper graph. And if you have a more frequent compounding period, that's also going to give you a steeper graph. So let's have a look at the options that we have here. So the first one is that, so here we've got a few different things. So it's got 5 and 10% per annum. And the difference is that they're going to be compounding, if you have a look, they're compounding annually or they're compounding quarterly. So let's have a look at the options that we have. So let's have a look at this first one. The first one here says that W is 5% per annum compounding annually. X is 10% per annum compounding annually, and Y is 10% per annum compounding quarterly. Well, if you have a look at the graph, well, this one is saying that W is the lowest interest rate and it's compounding annually. And if we just start by looking at comparing that with X, X has a higher compound interest and is compounding annually as well. But if you have a look at the graph, W is higher than X. This doesn't make any sense. So A is gone. Because W is higher, this interest rate needs to be bigger than this interest rate. The other thing is they've actually said that Y is 10% compounding quarterly. This is more frequent than the other two. And so that should mean that Y would be actually a lot steeper than the other two. But if you have a look, it's actually quite low. Y is growing at a very slow rate. So A is immediately gone. Okay, let's have a look at the next one. This one here, we've got W is equal to 5% per annum compounding annually. X is 10% per annum compounding quarterly. And Y is 10% per annum compounding annually. Now here, already, just by looking at W and X, 5% here is much lower than 10%, but not only that, X is actually compounding quarterly, which is a lot more frequent. So that would mean that not only is X going to be a lot steeper, it's going to be much steeper than W. So this one here is going to be out as well. Let's have a look at option C. Okay, we've got W is 10% per annum compounding quarterly. X is 10% per annum compounding annually, and Y is 5% per annum compounding annually. Now, if you have a look at this one, well, W and X have this higher compound interest rate, which is great. And if you have a look at both of them, they're much steeper than Y, which is great. That is a good start. We're much steeper than Y. The second thing is then, well, if you have a look, W is compounding quarterly as opposed to X compounding annually. And so W is compounding more frequently than X. And so this would mean that it should be steeper. And if you have a look here, W is indeed steeper than X. So here, this tells me that, hey, it might actually be C. So I'm going to just circle that, just to hesitantly now and check the final option just to make sure that it's not the right one. Let's have a look at the last one. Now, here, we've got W is 10% per annum compounding annually. X is 10% per annum compounding quarterly, and Y is 5% per annum compounding annually. So once again, they've got this Y is 5%, so it's much lower than the other two in terms of the interest rate. But if you ever look at the compounding periods for W and X is compounding quarterly, so it happens 4 times in a year, so it's doing it 4 times, but W is only compounding once. And so if you have a look here, X is not steeper than W, and so this one is also gone. This is out. And so our final answer is C is the correct answer. And so this is just identifying the graphs of compound interest for compound interest. Okay. So that was our compound interest formula and just identifying the graphs of compound interest. Now, with the compound interest formula, you actually need to sub in values into that formula, and it's sometimes a little bit annoying to do. There's a way that people can actually calculate compound interest a lot quicker, which involves just finding that future value interest factor. So here, this is where tables of interest factors for compound interest occurs. So if you remember, the future value interest factor is just this guy over here. So this 1 plus r to the power n, and then you just 1 plus r to the power n. This is just tells us how, if we just need, well, what number are we multiplying our present value by in order to get that future value? what we can do is if they give us the if they give us this future value factor, all we can do is just take out present value and just multiply it by this amount, and we will get the final future value. Now here, if you have a look, there's actually a note. We may need to adjust for compounding periods like we did earlier, other than annually. So with this, we still need to adjust R and N depending on the particular question. But this actually makes it a lot easier, and I'm going to show you with the question underneath. So this is from the 2011 General Mathematics paper. So an amount of $5,000 is invested at 10% per annum, compounded 6 monthly. And here we actually got a table of compounding values for $1. So what this means is, so just to help you read off this table, this is compounding values for $1. So what these values basically tell us is if I invested $1 at 1%, and they did it for 1 period, after that 1 period, it's going to be equal to $1.10. If I invested $1 at 20% for 6 periods, so they don't specify what that 6 periods is, it will give me $2.98 and 98.6 cents. That's what this table, that's how we can read off this table. This is just, you can think of all these values as just the future value interest factor for $1. Okay. What we're going to do is use the table to find the value of this investment at the end of 3 years. So let's just highlight a few things. First of all, we've got a bit of information. The first part is an amount of $5,000 invested. So what is this $5,000? That is just my present value. So P is going to equal to $5,000. So P is $5,000. That's my present value. That's what I start off at. The second thing is I've got an interest rate of 10% per annum. So here, that's R is going to equal to 10% per annum, or I can just rewrite that as 0.1 PA. Now the next part is they tell us that it's compounding 6 monthly. So the period isn't 1 year, it's actually 6 months. And so what we need to do is figure out how many 6 months are there in a year. There's 2 lots of 6 months in a year, so this is going to give me 0.1 divided by 2 per 6 months. Per every 6 months, the interest rate is going to be 0.1 divided by 2 per 6 months, and that will actually give me 0.05 per 6 months. So that's just me adjusting that interest rate to actually make it match up with my compounding period. The final thing is then I need to have a look at the rest of this. Use the table to find the value of this investment at the end of 3 years. This 3 years is the last part here. So what that tells me is that the value of N, the number of periods, is equal to 3 years. But if you think about the compounding period, so once again, we need to make sure that our number of periods matches up the compounding period. The compounding period is every 6 months. So we need to figure out how many 6 months there are in 3 years. Well, that's just the same as doing 3 lots of 2 sets of 6 months. So it's just 3 times 2. So that tells me there's 6 lots of 6 months in 3 years. Okay, so now that I've done all of that, I can actually just use the table and help me figure out what this is. So the future value formula, if you remember, was A is equal to P times 1 plus R to the power N. Now, if you note, so the present value is still $5,000, but instead of having to actually calculate all of this, which you totally could do, what we can do with this table is we can just actually, we can find this whole thing, this future value interest factor, that's going to be hard to say, from the table. So what we need to do is just all we do is we find our interest rate at the top. So here, the interest rate was 0.05. 0.05 is just 5%. So here, 5% for the 6 months. Then I look on the left-hand side and look for the period. So at the bottom here, I found that it was 6 lots of 6 months. And so I'm going to go to 6 lots of 6 months. And so all I need to do is just read off the intersection of these two. So when I intersect these two, it's going to give me 1.340. And so here, all I need to do is just multiply this 5,000 by 1.340. And so that gives me 5,000 times 1.340. That gives me $6,700. And so this tells me that at the end of 3 years, this investment is going to be worth $6,700 just by reading off the table. Now, you could also do this using that in our compound interest formula. So we could use our compound interest formula for this. So we could go, okay, the present value was 5,000. I'm going to multiply that by 1 plus 0.05 and do that to the power 6. And hopefully, we should get the same amount. So if I go 5,000 times 1 plus 0.05 to the power of 6, we get roughly the same amount. So this table is actually just like a rough estimate. So this will actually tell me I've got $6,700 and 0.48 cents. If you notice, these two values are pretty much fairly close. You're like 50 cents off, but this table is actually a quick way that you can calculate compound interest just by multiplying the amount by reading off this table. So here, what we want to do is we want to check what the interest rate is and make sure that we adjust it if we're compounding over a different period. So here we compounded every 6 months, so we have to change our 10% per annum to 5% per every 6 months or every half year. Then from there, we need to actually just read off the period. We need to change our period to match up that compounding period, just like we did in the previous examples. So here it said at the end of 3 years. And in this particular scenario, 3 years is just 6 lots of half years. And so once we've done that, we can just read off the table. And so find our interest rate at the top, find our number of periods at the left, and just match it up. And then multiply that amount by the present value that we're investing by. Okay. So that's how we can use a compound interest table to actually help us find compound interest. Okay, if we flip over the page, now the final thing we're going to talk about in this video is what an effective annual interest rate is. So when we want to compare, this is particularly when we want to compare different interest rates when they've got different compounding periods. So let's just fill in the blanks here. The frequency, so how often the compounding needs to be taken into effect when dealing with financial contracts. So as I said before, the more frequent that something compounds, the quicker your investment grows. And so even though two companies might be, let's say like two companies, one of them might be saying, oh, we've got 6% per annum compounded yearly. And there's another company that goes like 5% per annum compounded monthly. And so here, even though it's the 6% per annum looks bigger than the 5% per annum, if you have a look at the periods, this first one is compounded yearly versus this one being compounded monthly. And so what we want to be able to do is compare and figure out, hang on, which one is the better investment to actually make? Is the one that compounds more frequently, or is it the one with a higher interest rate? And so what we want to do is be able to do that. And this is where the effective annual interest rate comes in. So the compounding period also affects the interest accrued. So let's just talk about two definitions here. The first one, the nominal interest rate. The nominal interest rate is the annual interest rate that does not take the compounding frequency into account. So the annual interest rate that does not take the compounding frequency into account. So this nominal interest rate is just the amount that they tell you. So here, this per annum. If they don't tell you how frequently they're compounding, this like per annum interest rate is usually the nominal interest rate. So if you have a look here, compounding periods per annum must be specified, and the nominal rate must be divided by the number of compounding periods. So this is what the steps that we've normally been doing so far. Now the other definition that we need to know is the effective annualized interest rate. So what we do here is we convert the nominal interest rate back into a per annum interest rate. And so this is usually calculated per $1 and re-annualized back to 1 year. So what we're doing here is figuring out what's the equivalent per annum interest rate based on my compounding period. So for example, and so if we have a look over the page, there's actually a formula here. Actually an example to have a look at here. Oh, and I've actually done, pretty much got the exact same example. So I'm going to go through this example and then I'm going to actually leave it here for today's lesson. So let's just have a look at this one. So example 4, $1,000 is invested at 6% per annum, compounding half yearly. Okay, so we want to calculate the future value after this is the investment after 1 year. So if you have a look, so this is 6% per annum, compounding half yearly. So our interest rate was 6% per annum. But because it's compounding half yearly, we need to actually convert that to a half yearly interest rate. So every year has 2 half years. And so this is just going to be 0.06 divided by 2. 0.06 divided by 2 because it's 6% being divided into 2 half years. So that's my per 6 months interest rate. And so here, my per 6 months interest rate is going to be 0.03 per 6 months. And so here, for my formula, it's going to be 1 plus 0. Let me put this down, 0.06 over 2. And so that's just 1,000 times 1.03. So when I evaluate what's inside the bracket, it's just going to be 1.03. Oh, the other thing was, we want to figure out how many periods. So if after 1 year, so 1 year, well, how many half years is that? That's just 2 half years. So that's why here, instead of having it to the power 1, it's actually power 2. So if I actually calculate what this is, 1.03 to the power 2, this is going to be 1.0609. So this is 1.0609. Okay, so what this tells me is that the 6% per annum compounding half yearly is equivalent to, well, the annual interest rate is just going to be 6.09%. Just by reading off that end part here. So we ignore the 1 point and then we just figure out what the interest rate is. So the normal interest rate for this particular scenario was 6%, but effectively each year you're actually multiplying by 6.09%. Okay, let's have a look at this next example though. So let's compare it here. So $1,000 is now invested at 5.94% per annum, and this is compounded monthly. So here our interest rate is 5.94% per annum, which is 0.0594 as a decimal. But here it's compounded monthly. So what we want is to figure out a monthly interest rate. So what we're going to do is we need to take this 0.0594 and divide it by 12. And that is our monthly interest rate. Now, for some of these numbers, when they get really, really small and you put it in a calculator, it actually will give you scientific notation. I usually just don't prefer it. I'm just going to leave it in this exact form. Now, once again, we want to calculate the future value of this investment after 1 year. So 1 year is our number of periods. So 1 year, but because we're compounding monthly, we need to write this in months. And so here, this is going to be 12 months. So if you have a look here, this is raised to the power 12. And so in my formula for the future value, this is just going to be 1 plus 0.0594 over 12. And if you calculated this, this would be 1.00495. Okay. And so if we put this in a calculator, so that's hang on, let me do this in my calculator properly. So that's going to be 1 plus 0.0594 over 12 to the power of 12. And so that was an effective, so that will tell me that the future value interest factor is just 1.06104. Let me just cut it at that decimal point. Okay. So what this tells me is that if I'm investing at 5.94% per annum, compounding monthly, that's equivalent to, just have a look at this interest rate. So here, just reading that as a percentage, that's just 6.104% per year. So the nominal interest rate for this one was 5.94%, but because we were compounding that monthly, the effective rate was 6.104%. So out of these two, even though the first example, we had a higher nominal rate, because of the higher frequency of our compounding periods in our second example, the second example is going to has a better effective rate. And so therefore, 5.94% compounding monthly has a higher effective rate. So that's how we deal with this effective rate concept. So the effective rate is just what is the equivalent of your nominal interest rate for your particular compounding frequency. So that's it for today, Year 12s. We're going to have a look at a few more examples in our online lesson on Thursday, and I'll hopefully see you guys then. As always, stay safe, stay healthy, stay wonderful, and I'll see you on Thursday. Bye.